Well, hello, everyone. Welcome to Cloud Computing for Biology and Healthcare. Our speaker today is Chris Dotson. He's an IBM Distinguished Engineer and Executive Security Architect. Chris is the author of the O'Reilly book, Practical Cloud Security, and he has over 20 years of experience in the IT industry, as well as 11 professional certifications, including the Open Group Distinguished IT Architect certification. His focus areas include cloud infrastructure and security, networking infrastructure and security, servers, storage, and bath ponds. With that being said, I will hand it over to you, Chris. Thank you.
I do hope with this talk that you can come to see security in the cloud not as something to just be endured, but as a way to make your endeavors, whatever they are, more successful by avoiding a lot of security incidents, dealing properly with any that do happen. I do want to encourage you, please, interrupt with questions as they occur to you. It's actually easier and more interesting for me to answer questions than just to lecture. If you don't ask questions, you'll just have to listen to me lecture. So, let's get started. For those of you in the room, you can use the mics, and if you're on the chat, I will try to monitor the chat, maybe with some help to just take questions in line. So I do have a few slides, just because you can't give a presentation without slides, but they're not super detailed. I do want to talk just a little bit about principles and concepts. When you create an information system, either on-prem or in the cloud, one of the very first things you've got to do is identify where the good stuff is. In your case, it's probably something like protected health information. If you don't keep really good track of where it is, if it's in this database, on this virtual machine, and it's backup in an object storage bucket, if you don't know, you're kind of doomed to either miss something or waste a lot of resources protecting low-risk things. It's probably also super obvious, but it is impossible for someone to steal the data if you don't have it there. I've had people tell me before that you can't have privacy without security. My rebuttal is sure you can. If you don't collect the info in the first place, then there's no way at all that it can be stolen, even if the security is poor. That's not an excuse to have poor security practices, to be clear, but just sort of an admonition to not let data leak out all over the place if it's not needed or if it's not used there. So if you don't need it, don't put it there just in case. It's kind of the idea. One of the things that can help, by the way, in cloud is tagging. You're probably familiar with this with photos. You tag a set of photos as a beach trip, and then you can search instantly for all your beach trips, for example. If you are careful in cloud to tag all of your cloud databases or your virtual machines or your object storage buckets with the type of data that's in them, then it can be a whole lot easier to find them. And you can even write some security policies in some cases based on the tags. So when you're laying out the system, consciously try to keep your more sensitive data in just a few places, even if that means a little more work in accessing them, and tag those locations. That'll reduce your risk because it reduces the impact if something goes wrong. And speaking of risks, we should probably talk about a few of these foundational concepts. My apologies if these are already familiar with you, but I find there's a whole lot of confusion in these common terms, so I do like to cover them quickly. A vulnerability, as it says here, is a weakness in the system. Think of it as a place where something's likely to break. I tend to like to use bad analogies to explain things, so I'm not sure if it actually helps to communicate better for you or to remember it better, but I do find it amusing. So here's one bad analogy. If you've got a backyard, you've got a wall around your backyard, and you've got a tree growing up next to it that might allow somebody to climb over the wall, then that tree next to the wall, in that case, is a vulnerability. It might be a great feature, right? A lot of vulnerabilities in information security do come from great features, with ingenious people misusing those features for bad results. But here we are. The tree in this case is a vulnerability. A threat is something or someone that might cause something bad to happen using that vulnerability. So it's sometimes broken down into threat actors and threat actions. But in the case of the wall with the tree, one threat is the burglar might climb over the wall and get inside. And then a risk is the something bad that might happen. The risk is that you get your stuff stolen in this case. The risk is what we have to get to. It's all fine and good to talk about trees and burglars, but the real problem is I like my stuff and I don't want to lose it. So there's a lot of ways you can figure out how bad the risk is. We usually use the fancy term assessing risk, which is just running it through our process so we can prioritize dealing with different risks. It's important to do this because if we just wander around worrying about trees, which are great, but if we worry about trees growing next to walls, we might do stupid things like chopping down all the trees without thinking things through. Maybe it's better to accept the risk or trim one of the limbs off or put in a barbed wire or electrify the fence with 20,000 volts. Not legal advice, don't do that. But if we worry about burglars in the abstract without taking into account the context of the system, is there actually anything in the backyard you're worried about being stolen? Is that the important perimeter? How worried are we about someone in the backyard at all? We need to worry about the burglar in this system to prioritize risk properly. So the risk is what's important. The vulnerability, the threat are just ways to get to that risk. The best way I've found to think about risk is very simple. It's likelihood of the bad thing happening, and then the impact, how much it hurts if it does happen. So like in this analogy, how likely is it that a burglar will climb the wall and steal my stuff? If it's a 50-foot tall wall and the tree limbs start 15 feet up, then it takes a pretty talented or stupid burglar to give it a try. If it's an 8-foot wall with a nice easy climbing tree, the likelihood's a whole lot higher. And then next, what's the impact? If I got the crown jewels of England, for example, or protected health information that may be useful for identity theft or extortion or lots of other bad things, then the impact is a lot higher than if it's my old computer collection, right? The combination of likelihood and risk, that tells you how bad the risk is. To bring this back to cloud security, it's really important for us to understand what it is we're protecting. For us here, that's probably going to be protected health information, but could be regular personal information or something mundane but useful like cloud API keys. As an aside, people like to steal cloud API keys and then either run crypto mining on the cloud account, which costs you a lot of money, or launch other attacks from your cloud account. So you've got other risks besides the very important loss of personal health information. But you do need to know what you're protecting. You need to know what constitutes good protection for the cloud asset, and then you've got to think about the likelihood and impact to come up with how bad the risk is. I actually like this little drawing. You might have seen it before, but it's a good way to think, I think, about likelihood and impact. If something's really likely to happen, but you're just going to get your shoes wet, it's not a big concern. If it's really dangerous at the bottom, spikes and snakes and deadly things, the chances are really low, though, then it's not as bad either. The ones to focus on first to build the bridge or putting tooling or putting mitigations is when you have a high impact and a high likelihood. It's not that the others aren't important, but you might find that that's all you can do is to keep up with the high risks, depending on how many resources you have. I happen to use most of the time NIST 830 as the framework. It's a publication by the US government. It's not just for government work. Anybody can use it. And in particular, in this regulatory domain, you're regulated by HIPAA and so forth. It can be a good resource, but there's plenty of other good ones as well. To my mind, the key is to have them simple. So there's some nice tables in here. If you can estimate likelihood and impact, then the table lets you estimate the overall risk. It's not perfect, but the good, one of the good things is that since it's in a government publication, people don't tend to debate your methodology as much. So it is, of course, very important to note that this risk estimate is only going to be as good as your estimates of likelihood and impact. Garbage in, garbage out, right? So if you have really important stuff to protect, then you should get serious about improving your estimating skills. But even a simple estimation is a whole lot better than nothing, especially if you have an improvement process where you check to see if it was assessed properly as lessons learned after bad things do happen. So if you've got some risk estimates, what do you do about the risks? And again, this is not cloud specific. This is just general risk management, but I think it's important. For each one, each risk that you usually have about 4 choices. You can avoid it, right? Maybe you move all the good stuff somewhere else or don't store it at all. It's very effective, but it's not always practical. You can mitigate the risk. You can put in barbed wire, you can trim branches, you can mitigate the risk of the tree in ways like that. You can transfer it. You can make it somebody else's problem. Generally, someone else will want to be paid for this service, but not always. The classic example is you buy insurance and then they have to replace the stuff if it's stolen. I don't know if you can reasonably do that in the case of losing PHI because there's penalties, but or you can accept the risk. Yeah, a burglar might climb over the wall and steal my stuff, but the risk is low enough that I'm going to worry about something else. Maybe you've got an unlocked gate on the wall, so you're perfectly willing to accept the risk of someone climbing over the wall until you lock the gate. So that's risk management in a nutshell. You got to understand your vulnerabilities, your threats, and your risks in your environment. What tends to cause these risks, of course, are threats, as I mentioned, and usually it's usually people in our line of business, but it can also be earthquakes and similar bad things. There's a whole industry in threat intelligence. So strategic threat intelligence, like the major actors out there, their perceived motivations and their techniques, as well as tactical threat intelligence about what techniques and technologies the bad guys who are making the headlines are using these days. So I'm not going to talk a lot about threat intelligence here, except to say that there are some really great resources out there. IBM's own X-Force Threat Intelligence Index is good. The Verizon Data Breach Investigations Report, those are my favorites. They look at past data breaches from the last year and their causes. If you're in charge of designing the defenses, it's kind of good to know what the attackers have been doing recently. So, hopefully you have some idea of what threats you're up against, how to assess risks, and let's talk about some important concepts for reducing risk. Least privilege is one of those security concepts that's painful in real life because it can slow things down, but it is really necessary, although you can go overboard. If you tend to do it wrong, you'll get the kind of picture that's shown here, which you may have seen before. You put up the gate and then everybody goes around it because it's too big of a pain and it's too easy to go around. So least privilege, it means exactly what it says on the tin. Any access you give should be the least amount of access that you can give and still have things work. It's obviously very safe if nobody has any access at all, but it's a little hard to get work done. So this is a little bit of an art more than a science. And again, that's why it's under the conceptual area. Most people are familiar with the concept, and it's usually interpreted to mean that you don't just give everybody root or administrator access. That's good, but it is more than that. It certainly applies to people. It means that you only give privileges to people when they need them, but it also applies to automation. I can't count the number of times I've seen something like an inventory tool that just needs to read the information out, where that tool's got complete administrative access. So you've just made the security of the whole system dependent upon that inventory tool. And what's worse is you probably didn't realize it. Unfortunately, the bad guys are really good at spotting things like that and making use of them. The downside, of course, is that if you do it right, you have a whole bunch of different privilege levels to track, and then people with a legitimate need to do something get stopped and have to wait while they request more access. Most of the people that you're going to work with really want to get their jobs done. So paradoxically, tightening down least privilege too much can actually reduce your security because your administrators and users will find a way around the controls in order to get their jobs done, and they won't feel guilty at all because they'll think they're doing the right thing. So it is important to have least privilege. Don't take any of this as an excuse not to do it, but you do need to make it practical and usable, or people will just go around it. So please do not put in controls that look good on paper, but get circumvented or not usable in real life like this. In a cloud environment, by the way, there's a new source of really highly privileged access that's very easy to overlook. Whoever and whatever has access to your cloud account with the cloud provider has a lot of privilege. It's basically the equivalent to giving them like physical access to the computer room. So some people do have to have this, but it's amazing that organizations who wouldn't dream of giving 100 people root or administrator access then give a lot of people access to the cloud portal that would allow them to override the other protections. So again, part of this is deny by default. So by default, nobody and nothing has access, for example, to the cloud provider portal and the APIs, and you give out those permissions carefully as needed, but not so carefully that people try to go around the restrictions unless you're sure you can detect that and you're running a very highly secure system. Next concept, defense in depth, right? This is another term that you've probably already heard of, but think about this in terms of the threats you're up against. And the idea behind defense in depth is really simple. No control is perfect. So you'd like to be able to have any one of your controls fail and still lose the game. Not lose the game, I should say. In practice, it's not always possible, but it is a good goal. I've done a lot of security reviews, and a lot of times I'll tell somebody, well, you need to do X to keep somebody from who's trying to do Y, to block somebody trying to do Y. And one of the things that really annoys me is to hear, well, that's a waste of time. They can't get in to do that. Let me tell you, the bad guys have a funny way of ending up in places where they're not supposed to be. I most commonly see this, fallacy applied to network controls. Oh, we've got a firewall. The bad guys can't even get to that piece you're talking about. And that's true. They should not be able to. But if they do, and there's a large body of data in the DBIR and the X-Force reports that I mentioned showing that it happens a lot in real life, then you do need to have another control to stop them, or at least some way to detect them. So, I mean, here's another bad analogy, and bad art. Nobody's going to hire me for my design skills, I think. If you're the bad guy trying to hit a target, like your database of medical records or your user's passwords or whatever it is, but imagine the bad guy is an archer trying to hit a target. If you've got nothing at all in front of the target, then a fairly unskilled archer can probably hit it. If you put a wall in place that only has a few windows or openings in it, then the archer will have to get through that one control, that wall, to hit the target. That's a lot better. If you layer a couple of them differently, a wall and a net, or two walls that line up differently, all of a sudden this attacker better be Hawkeye to make the shot. It's still never going to get to impossible, but it gets a lot harder. If you're familiar with probabilities, then if the two controls are completely independent, and the chance of getting through the first wall here is 5%, and the chance of getting through the second wall is 5%, then you're down to 0.25% chance just by layering those two controls. And that's far better than need to control on its own. Note that this does not hold if those controls aren't completely independent. If you've got two overlapping controls that can be bypassed by the same thing, like stealing the same set of credentials, that's not really useful. But it is useful if they're independent, and it's often easier to come up with two 95% controls than one 99.75% control. I think medical testing uses a related concept, with less expensive tests with high false positives, more expensive tests with low false positives, and the combination of the two is better than a single test. It's usually not this precise in real life, but the concept is still there. So by putting in place defense in depth, you make your overall system of controls much more effective. Does that mean you should put like 8 layers in one place and leave a completely different target open? No, overkill is a waste of resources, but at least once you have, at least some coverage everywhere, then you should put additional layers where it matters, even if it seems like it's a little bit of a redundant effort. In cloud, that might mean that you encrypt really sensitive data in the database separately, in case somebody manages to get access to the database outside the application. And then also check access everywhere, even if a threat shouldn't get in through the perimeter by trying to access it. Also put in place a network perimeter, internal network controls, detection and response capabilities, so that you'll know if somebody's gotten through one of the other layers. In theory, any one of these might be able to block or detect the threat. In practice, you do have to plan for some of them to fail. So, next thing, shared responsibility. Now, this is something that a lot of people get confused about in the cloud, even people who've been using it for a while, and it's the shared responsibility model. There are a lot of distinct layers in most cloud environments, and people often get confused as to who's responsible for what. So one of the first big mistakes might be that thinking, and this is less common now, but if you rent a virtual machine from a cloud provider, then the cloud provider has to patch the operating system. That's not true, right? The cloud provider is going to patch the hypervisor underneath, but for most infrastructure as a service, you as the customer have to patch the virtual machine operating system. So another bad analogy, right, is pizza as a service. Now, the first version of this chart was by a guy named Albert Barron. I've added a few toppings to it. In this analogy, if you want pizza, you've got a decision to make. Do I want to make the pizza, or take and bake, or get delivery, or go out? If I make it, I have to do everything myself, but I get the most flexibility. If I take and bake, then the dough, sauce, cheese, and toppings are all done for me. I just have to use the oven and provide drinks and a place to eat. I won't claim I always use the dining table either. If I get delivery, I don't have to use the oven, which, given historical trends, is probably a good thing. And if I go out, almost everything is done for me. Note that that's almost everything. And that is what people forget in cloud. I still have to eat responsibly. If I choke on my food, that's really, really bad, but it's not the restaurant's fault. So if we go back to the real world and look at cloud environments, make it home, is like on-prem. You do everything yourself. I don't have that one on here, right? But you do everything yourself. You're not using cloud. If we map the rest to the cloud models, then we see all the cloud models. In all of these models, the provider is completely responsible for keeping the doors locked and the security cameras and fences and items like that on physical security, and also for the hypervisors for virtualized infrastructure. But for IaaS, the network's a little blurry because the provider has an underlying network that they'll create with network switches and so on. But you've got, as the customer, you've got to put the logical network controls in place. For IaaS, you've got to do the operating system security. You've got to do patching, logins, all that fun stuff. If you're using, what I like to call middleware, like an application server or database, it's going to have its own access management and vulnerability management. And then you've got your application itself. You've got to make sure it doesn't have SQL injection attacks and the like. And then finally at the top, you've got your data access security. Nothing's going to save you, and it doesn't matter how secure the underlying infrastructure, platform, or software service is if you don't use the service properly. Just like you can have the safest car in the world and then run it into a tree, you can have a very safe object storage and then you leave it open to the world. Or have an application that's extremely well written and then forget to disable application access to someone who left the organization. So access control is important at all levels, even with SaaS, software as a service, and you're going to have some responsibility there. You have to eat responsibly. Almost every cloud provider lays this out. It's usually pretty similar. The trick is that a lot of services don't neatly fall into one of these three columns, IaaS, PaaS, or SaaS. Particularly the line between IaaS and PaaS gets pretty blurry sometimes. It really doesn't matter. It doesn't matter what bucket you put something in. The important thing to know is for each particular service where the provider's responsibility stops, where yours starts. If there's a misunderstanding there, it's almost always the cloud consumer's problem and responsibility in the cloud consumer that has the security incident. So these are some important concepts. Please keep those in mind as you're designing your systems, and you'll be much more effective. There are far too many permutations, unfortunately, in cloud architecture. So it's really pretty much impossible to lay out exact specifics. So keeping these principles in mind, I think, will help you guide those decisions. So now, enough with the concepts. We'll talk, well, we're still going to talk somewhat conceptually, but we'll get a little deeper. It is a little egotistical, but I also often tell my managers that I can do anything, but I can't do everything. Put another way, we all have to prioritize what's important because most of the time we just don't have the time and money to dot every last I to cross every last T unless you're, really in a, organization that treats security as a very, very top priority and invests very, very heavily. Most of the time we have to do some level of trade-off. Even if you don't, it's still important to have some sort of data classification system so that we make sure that we protect the most important stuff appropriately. The idea of using classification systems, of course, isn't specific cloud or even computing, but you do need to have one. It can be as simple as low, medium, high, maybe even low, high in smaller organizations. I would say resist the urge to make it more complicated than it needs to be, and that's just a good general advice. But on the range of low, medium, high, on the right of this chart, sometimes you've got data that you have to be really, really careful with. I equate it to toxic waste, right? You have to keep people away from it. You have to wear special gloves when you're handling it, and you want to get rid of it as soon as you can. It's very valuable, by the way. I'm not saying it's not, but it is dangerous and should not be taken lightly. So things like protected health information, sensitive personal information like social security numbers in the US, different things around other parts of the world are considered SPI, credit card data, important trade secrets. This is all stuff that you want to keep really good track of because you don't want it sitting around where anybody who doesn't really need it can access it. Sometimes there are regulations or industry standards that tell you that you have to protect this data in very specific ways. On the other hand, sometimes regulations, and I'm looking at you, HIPAA, they tell you you have to protect it, but you don't really give you a lot of prescriptive guidance on how to do it. And the guidance they do give may not be as useful in the cloud because it was written in the 90s. So they just tell you that if you mess it up, you'll be paying a lot of money in fines or other penalties. At any rate, you got your most critical data. It's usually not too difficult to spot. And then you've got some medium data, internal use data, routine financials, things that might be useful to an attacker for figuring things out, but not quite so bad as the high or other business data. Probably a lot of your data falls into this category in most systems. And then on the left-hand side of the chart, you might have a low classification where you can do very limited things. Maybe it's even things you don't mind having public. It's going to be specific to your organization and what you're trying to accomplish. But all of this is really the same, whether you're dealing with paper files or on-premises environments or cloud. However, here's where cloud platforms can help with keeping track of your data. In cloud environments, you can tag resources like virtual machines and databases and subnets. I mentioned this before. And then you have automation that makes decisions or performs checks based on these tags. So at a minimum, I would recommend that you tag any cloud assets that might either hold your highly sensitive data or have access to where it's held. Just because something doesn't actually have access to that data, that doesn't necessarily matter if it can be, if it can access the data, then it needs to be recognized as a bigger risk. It doesn't actually have to hold it, is what I was trying to say. So if you start seeing that everything's tagged as having critical data, you might want to ask yourself if it really needs to be, because it's often a good indication that you're not following the least privilege principle for system-to-system accesses. If basically every system you have gets full access to, your crown jewels. Another thing is that these tags do need to be uniformly used across the organization or across the whole company if possible. Sometimes that can be politically difficult, but if everybody uses different tags, then any automation depending on tags is going to be more complicated and it's going to be more failure prone. If you're provisioning cloud resources using automation, like scripts or Terraform or CloudFormation, things like that, which by the way are great techniques to have infrastructure as code, because with cloud you can just spin the stuff up. You can have the system spin all the stuff up all at once, remove it, recreate it. It goes for recreatable builds and infrastructure. But if you have those, it's a great idea for the automation itself to tag the resources as they're created, and that way you get some uniform tagging. You can even search through to find untagged resources, which might gotten there when they're not supposed to. Might be rogue resources. So some cloud platforms actually even let you put in access controls based on the resources tag. So you might say that like Bob can only administer systems that are tagged with data class low or environment development or whatever. I pick on Bob a lot. My apologies if any of you are named Robert. Tags are usually a key value pair. So you usually get the option to say this key, this value. So that's the basics of data classification and tagging. You do a little prep work here before you get started, and it can reduce the chances of, oh gosh, we had no idea that data was even stored there during a security incident. So next, let's take a look at some ways to protect that data, and let's make a side channel or a side track through HIPAA. I did mention HIPAA, and it's going to be important to you, so I'll spend a few minutes talking about it specifically. HIPAA was created in the 90s and early 2000s, before cloud computing took the world by storm. And in my opinion, it's a bit vague, vague and dated. My opinion doesn't matter, of course. It's the law of the land in the US, but it can be difficult in some cases to figure out what it's requiring. It's a little further complicated by the fact that it is just a law. So there's no certifying authority where you can go take a test and pass and now you're fine, as there is with some types of requirements. It's a little more reactive, and then if you mess it up, you can be subject to penalties. So there's a whole bunch of parts of HIPAA. It's an overall, it has a lot to do other than security. I'm just going to focus on what's called the security rule is relevant for this, and more specifically the technical safeguards. You can also read up on the administrative safeguards. These are things like having somebody named as responsible and having written policies. Those are very important also. And there's also a physical security part, which is one of the things that's actually one of the few things that you can completely offload to your cloud provider in a cloud environment. They have to run the buildings and the guards and so on. So I want to focus for a minute on some of the technical safeguards. One of the resources that I find helpful here, actually, Health and Human Services has a page providing guidance on HIPAA and cloud computing. It does have some frequently asked questions about when you need a business associate agreement with a cloud provider. So most major cloud providers will offer these. When you're allowed to store PHI on cloud and other things like that. The net from that is that you can store PHI on most clouds if you protect it properly, and if you get a business associate agreement. You don't need a BAA if you're just transmitting the data with no permanent storage. So like the telecom providers, you don't necessarily have to have a BAA with them in most cases. All this, by the way, not legal advice. I'm not a lawyer, but I have run cloud services that handle PHI. So you don't need a BAA if you're just transmitting it, but otherwise you do need one. It is important to look at this Health and Human Services page, just because a strict reading of the law might lead you to think that you can't, for example, use multi-tenant hardware in a cloud because it was written before that. You can, that page lays out that you can, as long as you protect the data. Another useful resource, I think, for understanding the specific requirements of HIPAA, although it's also dated and it doesn't address cloud specifically, NIST has another special publication, 800-66. If you just Google for NIST and HIPAA, you'll find it. If you spell HIPAA correctly, most people seem to put two P's in it like hippo, but it's not HIPAA, obviously. Like most NIST publications, it is a bit dense. It often requires several readings, and it links everything back to the rest of the NIST universe in risk management and the catalog of controls. But it is fairly well thought out and complete, as most of the NIST publications tend to be, in my opinion. The net with the NIST publication, and again, glossing over a ton of important specifics, although we can talk about some of them here. The net there is that you do need to protect the PHI by carefully controlling who's got access to it, making sure that you've got audit logs on who accessed it, making sure that nobody can tamper with it, make sure you encrypt it when transmitting it. It actually just says protect during transmission, but these days that almost always means TLS, and encrypt it at rest. So there's some fairly specific things that are called out in the security rule that you need to implement. Several clouds do also have specific guidelines for complying with HIPAA and with workloads in the cloud. Those can be very useful, but they're often fairly high-level guidance rather than like a very specific cookbook. So don't go in with the expectations that they're going to give you step-by-step instructions. They would if they could, but there's just so much difference in workloads that are being put on cloud that it's not really possible. So talking about protecting the data, there's several good ways to do that. I'm going to talk first about protecting the data that's at rest, that you're storing. You've got tokenization, you've got de-identification, and you've got encryption that are tools in your toolbox to protect the data or make it less risky to have. There's often some confusion between tokenization and encryption. They're both ways to protect data, and they're often used together. Encryption is like locking the data up in a box. It's still there, but you need a key to get to it. Tokenization, on the other hand, is when you replace a piece of data with what's basically a placeholder, a token. When you need the real data, you take that token back to a well-protected place, the token service, to exchange the token for the real data. Tokenization isn't generally reversible unless you've got the token service. You can't take a token and perform some mathematical operation to get the original piece of data back if it's done right. So you do have to rely on a secure token service. It's got a table with the token value and the real value. Tokenization is often used with credit card numbers, so they're a great example. The system will store a fake credit card number that only when accompanied with some cryptographically signed verification info that has the date and the time and amount will be processed like the real number. But the system doesn't actually have the real number, which can be used without all that verification stuff anywhere. Only the token service has it. There's other implementations of tokenization, like using a token in place of a patient identifier and things like that. There's often pre-built and tested solutions for doing this. As an aside, building your own cryptographic and tokenization implementations is often very dangerous. They're very finicky, especially the encryption implementations, and a tiny implementation issue can break the whole thing. I'm not qualified to design or implement crypto systems. Very few people in the world are. I doubt most of you are either, unless you've devoted a lot of your life to it. So please do use tested implementations to actually do the encryption. Tokenization is a little less finicky as you're replacing real information from a randomly generated token. As long as you're kind of careful to use a random number generator seeded properly, it's a lot easier. De-identification technologies are also an important way to protect the privacy of any individuals whose data you're storing or processing in the cloud. If you don't need that to be tracked back to individuals, then you can use de-identification to make it difficult to link it back to an individual. It is a large, complicated field that kind of deserves its own detailed discussion, but there's plenty of overlap here with de-identification and encryption and tokenization. Performing de-identification correctly can be tricky. Researchers have managed to link data that was supposed to be de-identified back to individuals in some cases. So you do have to be careful. That said, in some jurisdictions, and I think the US is one, although again, not a lawyer, but there are some jurisdictions where there are accepted safe harbor items that you can remove from your data to de-identify it, and then that sharply reduces your risk of both privacy concerns and of being held legally accountable if you've done those things. If you've done those things, it may not always protect you, but in the eyes of the law, it shows that you were at least diligent. So that's a really brief intro to tokenization and de-identification, and hopefully just enough to let you know if it may make sense to use in your environment. I do want to talk a little bit more about encryption because you'll almost certainly use that in a cloud environment. So as I mentioned before, encryption is like locking the data in the box so that you need a key to get it. And there's three main types of encryption that get used here. You've got encryption in motion, where you make the data going across the network unreadable to anybody snooping on the network. This is usually not too difficult. There's libraries. TLS is widely accepted. There's libraries to use. Almost everything can talk TLS. Just use it. Do manage the keys properly so that if you don't manage the keys properly, then anybody just snooping in the network might be foiled, but anybody who has the ability to actually manipulate network traffic can play man in the middle and get all your data anyway. So encryption in motion, not usually too difficult, just do it, right? Nike. Encryption in use is where the data is encrypted while the computer is using it, actually, in memory, and then it can only be used by one process. And this is still relatively new. I mean, like IBM mainframes have had something like this for many years, but Intel has an enclave, AMD has an enclave. It's built into the firmware of the chip. It can be a good control to guard against some kinds of attacks where the attacker gets administrative access to the system, but doesn't have access to the particular process that's using the encrypted memory. So if you go in and you get root access, you can usually just dump out all memory and you can see everything in it. This actually protects against even that attack because only that process has the decryption keys for those areas of memory. It does require support in the hardware using. So it's not in super widespread use yet in cloud environments, although most cloud providers do expose it now. So it's a matter of time before it gets more popular. The most likely thing to have to deal with, though, is encryption of data at rest, and that requires a little bit more thought. That's when you encrypt the data that's sitting on your media, like your disk or your tape. Tape's still used sometimes, although not in most cloud environments. Encryption of data at rest is a great control to guard against a lot of different types of attacks, but again, the devil's in the details. It won't guard against all attacks. So just remember the encryption at rest is not just a checkbox. There's lots of ways to check the box of encrypting data without actually reducing your risk very much. In a lot of poor implementations, as an example, you encrypt the data and then you leave the key to decrypt the data unprotected right next to the encrypted data. So that's just like locking a door and then hanging the key on the peg next to it on the outside. So that's why proper key management is very important. One kind of key management you can do here is that you can encrypt the data actually before you hand it to the service. So you give the service the encrypted data and not the keys. So I call that bag of bits, right? The service is just holding a bag of bits for you. Assuming you used a good encryption algorithm and implementation, you didn't give them the keys, there should be no way for them to read the data right now. Computers get better, implementations and algorithms are found to have problems, so that might not be the case forever. But since the service can't do anything with this data at all, no searches, no processing, nothing, the bag of bits method is mainly useful for things like backups to the cloud. Key management's easy. You've got the key, they don't, right? Just make sure to keep a copy of the key in a safe place, like a physical safe in a different location, because if you do lose that, nobody can get the data back if you've chosen your algorithm well. Assuming that the cloud service actually needs to work with the data, which is the majority of the cases, then your key management needs to be a little more complicated than having a physical safe. In cloud, that's often a lot easier than it is on premises, actually. So on-prem, you have to set up your own key manager or hardware security module and get everything talking to it. You can do that in cloud too. In cloud, the provider usually has these ready for you to use, and most of the services that store data already know how to talk to it. So you just have to turn it on or use it properly instead of building something. Specifically, there's usually two general ways that you can, there's usually two ways you can manage keys. You can either use a key management service, right? Which is multi-tenant. Lots of customers all use that same service. Or if you want more security and higher cost, you can use a dedicated hardware security module. That's usually a physical device, and it's certified to a standard called FIPS 140-2 or now 140-3. It's got tamper-resistant controls built into it, like case sensors and radiation sensors and all those types of things, so that even if someone gets physical access to it, it should be really difficult to get the encryption keys out. Unless you're working for a government agency or bank, you probably won't need to go with a dedicated HSM route. It's more expensive and harder to set up. You can generally safely use a key management service that your cloud provider runs, which itself will then use an HSM to store important keys that it uses to work. So you've got your key management service or your HSM, and you want to use it. Generally, what you do is you need to tell the cloud services that are holding your data, things like virtual disks and databases and services like that. You've got to tell them that you want to use the key management service. It can be as easy as, for this database, please use key number 123 in the key management service. Note that you usually can't do that later, because all the data would need to be re-encrypted, which means rewriting the entire database or disk. So that's why you need to think about that ahead of time. It often needs to be done when you create that resource. If you don't tell the cloud service anything, it's probably not going to encrypt at all, or it might. Nowadays, they'll usually encrypt the data using the key that they create, or so that's called provider managed encryption. That might be okay. You might not actually need to do anything to get the level of protection that you need, but you do need to figure it out based on how important the data is to you. So do it consciously. And nowadays it's pretty easy to just set in, create a key management instance and then point it at, one of your services at that key. I do want to take just a brief moment on algorithms and implementations, because there's a lot of confusion here sometimes. An algorithm, by the way, is a specific way to encrypt data. The most popular one is AES, Advanced Encryption Standard. An implementation is when a developer actually sits down and with a favorite programming language and makes AES happen. You've got to use both well accepted and tested algorithms, and also well accepted and tested implementations of those algorithms. As I said earlier, you don't want to be designing your own algorithms or implementing yourself, because a tiny mistake can ruin the whole thing. If you want to know what algorithms are considered good at this point in time, there's some resources like NIST 800-131A. And then if you have a regulatory requirement to use certified implementations, then you have to look for something that's FIPS 140-2 or FIPS 140-3 certified. You usually don't have to do that unless you're in specific regulated industries that explicitly require FIPS for it. By the way, you can generally use uncertified algorithms in your environments, even in those regulated environments. It's just they don't count. They don't count as a control. So you can use it, but you can't use it to meet the requirement of having encryption. Right now, almost everything uses AES 128 or AES 256 for data at rest, as a symmetric cipher for data at rest. These are fine if the implementation and the key management are done properly. So the net is knowing what data you've got, choosing what protections, tokenization, de-identification, encryption makes sense in your environment. Choose those and then use them. Even if you're using tokenization or de-identification, you'll probably still want to encrypt your data at rest and in motion. Do proper key management to be effective. But in many cases, you can use the key management service and built-in encryption in cloud services and get a really good level of protection. So speaking of cloud services, I've batted around a bunch of them, but I do want to talk for a moment about the types of assets and the security implications for those assets that are on cloud. There's a ton of different types. There's more coming every day. It's very confusing in a lot of cases. I tend to bucket them into like 3 types. So the 3 large buckets that I use, and there's probably other ways to classify them, is I use compute assets, storage assets, and network assets. So compute assets are things that run code, right? And a given service might be a mix of those things. You also have software as a service offerings, which you just use that directly. So I guess that's maybe a 4th type of asset. Usually you just think of those as applications rather than cloud assets. So compute assets, they run code. Storage assets, as the name might imply, store data. So it might be that the same assets would do both compute and storage. A lot of times they're split up now. So The storage is often a separate unit, and you provision the storage and then tell the compute to use it. And that can help from design, operations, and security. And you've got network assets, which let everything else talk. For compute assets, the most common thing that we think of is virtual machines, which have a whole operating system, kernel, and user space programs. VMs in the cloud tend to not have their own persistent storage. So you usually have to hook up a storage asset, as I mentioned, to store the persistent data. Some providers also provide bare metal machines, which are usually more expensive and slower to provision, but they don't share the physical hardware with any other customer. Given how many hardware level security issues have been discovered over the last few years, Spectre meltdown, zombie load, Riddle, Fallout, and so forth, using bare metal can mitigate some of those risks, but you need to determine if those are important risks for your environment. But they can let other people running on the same physical hardware snoop on your stuff and sometimes manipulate it. Rowhammer also. So aside from this, from a security perspective, these are about the same as virtual machines, but you may also be responsible for keeping your firmware up to date on bare metal machines. So you might have a little more responsibility. And then another common compute asset, which is very popular at this point, is containers. Containers are just like virtual machines in a lot of ways, but they don't have their own kernel. They're running on the same kernel as the host. They may have a full set of user space programs or even very little or just a single executable. And then you also have these application platforms as service offerings. So Heroku, Cloud Foundry, things like that. Code Engine. You could add things like serverless and so forth in here. So you usually deploy assets like build packs or actual application code into an application path. And what you track here will be specific to the past, but there's usually deployments of some kind that makes sense to track. So, you might track each of your instances of that. For compute assets, you usually have to worry about access control because anybody who gets access to the VM will get access to all the apps and data on it. You also have to worry about vulnerability management because one of the layers under your control will have the potential for vulnerabilities. So storage, there's a ton of different types of storage assets in cloud. I'm going to concentrate mainly on the first 5 here because the other types are kind of specialized variants of those. Block storage is just the cloud version of a hard drive. So you got data available in small blocks, like 16 kilobytes, made it available to the server the same way a hard drive does. File storage is just the cloud version of a network share. So NFS, CIFS, SMB, those types of things. For both of those, the primary concern is access control. Who's allowed to get access to the share? All other access control is done by the operating system. So for the storage asset, we mainly worry about access to the block or file storage instance. You do also have concerns over encryption in a lot of cases because a lot of those protocols either don't offer encryption or the encryption has a very heavy overhead for some of them. But the biggest thing to worry about is making sure that you don't accidentally share it out to people who shouldn't have it. Object storage is a lot like file storage, but there's no hierarchy. And you can attach a lot more useful metadata to the files, and the cloud service can control access rather than depending on the operating system to do it. So it's a really popular way to store data in cloud, S3 buckets, and lots of things are S3 compatible. And so you can get sort of a file at a time rather than like a folder share at a time. You've got databases and queues. So there's tons of different flavors for these, depending on what types of things, what your workload looks like and what your data looks like. You can have access control ranging from a single credential to access everything, like for some in-memory databases, like Redis and Memcache, or none. In case of Memcache, unfortunately, that was the case. That led to a lot of problems. Or you can have very fine-grained access control in the database. Sometimes these things run code also, like stored procedures, but they're mainly storage. For storage as a service offerings, you're almost always just responsible for access control. So the vulnerability management of the service is the provider's problem. Now, when I'm talking about databases, I'm talking about a database as a service here. So if you provision a virtual machine and install your own database on it, then you're using a compute asset and a block storage asset, and you're going to have to do all the vulnerability management on the compute part. But for everything else, the provider takes over a lot of that responsibility for you. The other storage types listed here are often special purpose databases in some fashion. So your responsibility as a consumer is going to be mainly in controlling the access properly there too, which is not to be taken lightly. it is good to know that these are available for use in a solution because you can reduce your risk when you don't have to deal as much with vulnerability management. So we talked about compute and storage, so network. Virtual private clouds cause people a lot of confusion, but they're typically a network construct, and all it really means is that a VPC is like a container to hold lots of different subnets that you attach your resources to, like virtual machines or your as-a-service databases or so on. So you can have multiple VPCs with most clouds, and then the subnets in one VPC can't talk to the rest of them or the rest of the world unless you explicitly configure them to. So in the old days of cloud, everything was just internet facing with one IP. With modern clouds over the last decade, you can now have things that, virtual machines and other assets that are plugged into different networks with lots of potential controls between them. You do want to be able to keep track of these types of things, like for feeding into your scanners, so that you can check for vulnerabilities, network vulnerabilities. Content delivery networks are often made for making assets quickly available around the world. If you want to track when you're using these and control access, because people hijack these and use them to distribute malware or other nasty stuff. DNS records, you want to make sure that you know what DNS records you have. Make sure that somebody doesn't get unauthorized access to your DNS system, because then they can direct your users to an attacker's site instead of yours. Of course, TLS should prevent this, but as we've talked about, it's good to have multiple layers of security. And then TLS certs. Lots and lots of outages happen because people accidentally let their certificates expire. So don't be like that. Do track your certs, make sure you refresh them properly. Newer technologies like Acme and Let's Encrypt and so on you can set up jobs to automatically renew them periodically, which is a lot safer than, because you're recreating the private keys more often in case they're stolen, and a lot less maintenance. The important thing to note about that is, like, Let's Encrypt is really just doing domain verification, as it's called. So if you own the domain, or if somebody takes over the domain, you can get a cert for it. One of the things that people pay more money for some of the providers for, arguably, whether, you can argue whether or not it's good money or not, but pay a lot of money to actually validate that there's like a real organization with a real person and that they're authorized to get that. So there's also organizational validation and extended validation certs. But regardless of which type of certs you get, you do need to track them, make sure you keep them up to date. So we've talked about the different asset types, and now let's talk a little bit about vulnerability. I did mention tags before also. So like one of the obvious tags that you might have is like data classification for stuff, but you can also use function or environments or so forth. Asset and vulnerability management. So it's time for another bad analogy, sorry, but I do like to think of asset management like a plumbing problem, and you're trying to prevent leaks in the system. So a leak basically ends up being an unknown risk. So it's a risk that you're accepting and you don't really know anything about it. And we don't want those. We don't want it all over the floor. We're going to have some risks, but we want them nicely in the little bucket over to the right. So one end of the pipeline, you've got your sources, your IT stuff, and these are usually your cloud providers. You're often going to use more than one cloud provider, right? So you want to know all of them. You want to make sure you're aware of each one. And if you're in a larger organization, or even a smaller one perhaps, you can find out about them through the procurement system somehow, or by watching people's credit card statements or network monitoring or something. But you've got to have some way of knowing what providers are in use. So you've got all these little IT supply pipes coming in. If there's one you don't know about, you've got some unknown risk leaking out all over the place because it's not feeding into your inventory systems. You're just unaware of it. There's lots and lots of types of assets. So everybody thinks about virtual machines, but you might also have containers, serverless functions, PaaS instances, storage network, and so on. So if you can have a leak by not knowing about the provider. The second place you can have a leak is when you know about a provider, but you don't actually pay attention to all the different assets from that provider. Maybe you don't see all the accounts. Maybe you don't look at all the assets in the account. So then that leaks out all over the floor here in this second spot where you could have a leak. These types of leaks can happen pretty easily. You might not have a double check process to make sure the automation is actually running. There might be a flaw in your automation. You might be trying to do it manually and missed it. or other things like that. So you do want to design the process to where a single human error can't cause a huge leak here. If you get rid of these first two types of leaks, then in theory, you've got a pretty good inventory of what you've got. Now, from your inventory system, of course, you're going to feed out assets to do different things. Like you might have a network vulnerability scanner that runs. You might have code scanners that run against code, DAST and STAS scanners that run against the code you've got, other types of tools that we can talk about. But one of the main reasons you use an inventory is so that you can use it to prevent and fix issues. So another place that you have a leak here is that you have that tooling and you don't use it to check everything. So, and that's also going to give you a bunch of unknown risk at the top. So in terms of providers, lots of cloud providers actually have some built-in inventory systems that you can use for this, by the way. You don't necessarily have to have your own database of stuff. So for AWS, there's AWS Systems Manager. For Azure, you've got Azure Information Security. For Google, there's Cloud Security Command Center, Asset Inventory. IBM's got, the IBM Cloud APIs and Portal and Security and Compliance Center and so on. So each provider does have some options for tracking inventory that can probably do some of this job for you. But now that we have the inventory in the middle of the pipeline, we've got to do something with it. So you feed those assets into your tooling. If you don't feed all of them in, you've got a leak. You just simply don't know about some security issues. That might mean you have an asset on a network you're not scanning, or a web application you don't test, or a system that you don't check the configs on, or a Windows system that you're not running antivirus on. I consider these tooling leaks, and you need to have some feedback from your inventory system so that when the tools run, you see which assets are getting neglected. And then the final place where there's a lot of times there's very large leaks is when you have a finding and then you ignore it. Now, look, it's okay to consciously accept the risk and decide not to fix something. That goes into the known risk bucket. What's not okay is if you have a leak in the process, one of your tools is spitting out findings and you're just not looking at those at all. It's not really like news or complicated, but detecting vulnerabilities doesn't actually help if you're not going to do anything about them. So in addition to the network controls, this is one of the contributing factors that happened to Target, 8 years ago now. The intrusion detection systems and the antivirus findings were both all the way in through the system, and the findings were just falling out at the bottom and nobody was paying attention to them. So that's how I think of the asset and vulnerability pipeline. You want to get all your assets in and run all your tooling against it, and you want to spot any leaks in the system. So switching tracks a little bit here, let's talk identity and access management. IAM is probably tied, by the way, for vulnerability management on keeping your assets safe, in my opinion. So all the firewalls and patches in the world won't help you if an attacker can come right in through the front door through administrative entrances and use valid credentials that have been stolen or leaked. So IAM's even more important in cloud environments than on-prem because it's harder to establish a network perimeter in a lot of cases. You can, but you have to be careful. Although depending on the network perimeters, the only control was a bad idea long before cloud technologies were popular, to be clear. But it does exacerbate the situation a little bit. So there's actually two central pieces to IAM, as you might guess from the name. The first is identity, and checking the identity is called authentication. The second is authorization. So that is, after I know who you are, am I going to allow you in or not? So I think bad analogy 5, I'm losing count, 4 maybe. If you want to go and enter a military base, you go up to the gate and you present your identification. The guard looks at your ID, compares the picture with your face to see if it's valid ID, maybe uses a little ultraviolet light or checks other security messages on the ID to make sure it's not fake. The guard authenticates you. At that point, the guard may believe that you are who you say you are. You're authenticated. But if you're not on the list of people who are supposed to be allowed in, you're not going to be authorized to enter. So these two concepts are often confused. We often implicitly authorize and allow in anybody with a valid ID, or we revoke all access by tearing up the ID, but they're really two separate things. And in cloud environments, a lot of times that's important because you'll have an identity in a lot of cases, but not be authorized for things. So it's important to talk about the whole life cycle of identity and access management. Now, for a lot of teams, the process to request access And this may be okay in some cases, but the process to request access a lot of times is ask Bob and he'll give you access. So longer term, that leads to a mess, right? You end up with access strewn all over. Nobody really knows like why all the IDs are there or why they have access. Unless you've got a really small team and you can actually keep all the identities and required access right in your head, you do need to have a process for requesting access and for approving it. Also, depending on the regulatory regime you're in, you may be required to show those records to prove that you're doing it, right? So even if you do have a small team, it's also easy to forget to revoke someone's access when they no longer need it. And successful teams do often grow larger over time. So even though it might be something you can keep in your head now, it might not be in a year. If you're doing a great job and the team grows. So you do need a process or even better automation to revalidate access periodically. And that's why the other parts of the identity and access lifecycle, besides just authentication and authorization, are important. I have seen a lot of security incident where the attackers got in via access that should have been revoked a long time ago, or never should have been granted because there wasn't really a need for it. And this is really important in cloud because in a lot of cases, things are open to the internet. And so access control and detection are the only layers that can keep you safe in those cases. You can ask 10 experts and probably get 10 different opinions on the detail, but I prefer a very simple view of this IAM lifecycle. First, somebody requests access, usually with some justification, but maybe sometimes it's implicit. Second, that request gets approved by someone else, I should say. You don't self-approve, right? So in some cases, you might automatically approve all the requests, but in a lot of cases, you want at least one person to approve it. Then third is the identity or access gets created. Sometimes a human has to go do that. It's better if it's automation. Fourth is you actually use that access. So authentication and authorization, certificates, password, keys, and so forth. And the system either checks against a distributed or centralized list to authorize you. And then finally, you have to revalidate it periodically. So some types of revalidation should be done really often, checking nightly to see that someone you had to fire doesn't still have access, for example. Other types of revalidation can happen a lot less often. So I usually recommend quarterly, but you should ask if the access is still needed and revoke it if not. The entire life cycle does work a whole lot better if it's easy and fast. So people tend to hoard access and cling onto it. If it took a week and 3 approvals to get it, they're much more likely to only request access when they need it and not throw a fit if it's revoked, if it's easy for them to get back if needed. So low friction is fairly important here, but of course you do still have to like make sure that you're not just willy-nilly approving everything. You do want to back up for any critical systems, and access control is no exception because it is a critical system for keeping the systems running and fixing problems. So you can cause or you can extend outages if authorized people can't get the access they need during an incident. In fact, as soon as that happens once, if you're in charge of the access management, you can probably kiss the rest of your access control plans goodbye because they're going to get ripped out in the name of keeping things running. So you do have to have some backups. You need usually this means an emergency break glass or fire call method for getting access. And one popular or reasonable method for doing it is having one or more privileged IDs that are available for checkout in a hurry if the regular access control methods aren't working. It's great to have the emergency access methods, but they need to be noisy, rarely used, and they need to maintain individual accountability. So noisy meaning that several people should know that the emergency ID is being used and ask why, so that it should be very difficult for somebody to use it secretly. Rarely used, of course, because if you're like sweeping up glass off the floor from a break glass process every 10 minutes, you're not going to pay any attention to it. And individual accountability so that you can tell who actually took it and did something. So cloud identity services, you may need to authenticate also this again, right? If you make it too difficult, people will tend to work around it. So there are lots of different ways and places that you need to authenticate people in cloud environments. So you might have to authenticate administrators. You might have to authenticate end users to an application, to a database. Some of these are new, and then some of them are similar to on-premises deployments. So like the Cloud Portal API and the Cloud Portal and the Cloud API are kind of new in this environment in cloud, but similar ideas. So there's several different types of cloud services that can be used for authentication, and it can be a little confusing. So first thing is you've got the, I'm sorry, I missed that. First thing, you've got the cloud provider system for using the cloud itself. So it's called various things like IAM or cloud identity. This is the system that humans use to authenticate so that you can actually log into the portal to provision systems, to use cloud services, things like that. Humans usually, even still today, log in with the username and password, and then hopefully some other authentication factor like a hardware key, or a one-time password. We'll talk a little bit more about multi-factor access in a minute. In addition to logging into the portal, part of every cloud IAM system is API access, which uses an API key. An API key is kind of like a password, except it's not intended for humans to be able to remember. It's not a memorizable secret. It's used for access automation. For that reason, it can be a long string of random gibberish, and it can be practically unguessable if created correctly. So second is you've got cloud identity services that let the end users of your cloud application authenticate. And that's usually different. So you usually don't use the same system for people to log into the cloud portal as you do for your end users to log into your app. These end user systems are often split into different types, like business to consumer or business to employee identity systems. And the difference is that like the consumer identity systems, if you're talking to like end users, the general public, those will often let you use like social logins like Facebook, Google, or LinkedIn or things like that. Whereas business employee systems, like they usually, tuck in their virtual shirts and be serious and concentrate more on letting you log in using existing company credentials. Another confusing thing, by the way, is that the names of these identity systems often don't give you much hint of what they do. So Amazon calls theirs Cognito, which I guess is a nice pun on incognito, which I appreciate, but it's a little hard to, figure out what they're talking about. Google inexplicably calls theirs Firebase, I think. So who knows, what that means. So there's several different identity service providers that aren't infrastructure providers too. You may have heard of Okta and Ping and Auth0. All these can be ways that you can have an identity system to allow your users to log in. The important thing here to know is that creating your own user and password repository and validation systems can be a little tricky. You do need to know about the proper ways to hash passwords using things like PBKDF2 or scrypt or bcrypt. You need to be very careful on how you store them and verify the password hashes. Like if you just store a list of people's passwords in a database table, you're probably going to have a bad day at some point when somebody steals that table. This is how credential stuffing attacks happen, which probably some of you have had happen. People get lists of like usernames and passwords, like email address, and this password was used on LinkedIn, for example, and then they'll just take that username and password combo and just try it everywhere they can to see what they can get into. And if you're really unlucky and you use the same thing for your bank as for LinkedIn, then you're going to have a pretty rough time. So there have been lots of oops, we leaked all of our passwords breaches in the news. End user identity services are probably a better way to go for most organizations. So let's see. I'm not going to cover a whole lot about federation and single sign-on at this point, but it is important to note that I can have an identity one place, I can have an identity another place, but I can use like a different thing to authenticate me. And that goes back to like the social logins. Like if I log into a site with LinkedIn and I'm, Chris at Dotson97.org, I log in there, I'm actually got a different ID on that system than from LinkedIn, but that system is trusting LinkedIn to authenticate me. And so that's the general gist behind federation and single sign-on. Let's talk a little bit about authentication specifically. Everybody's familiar with passwords. One thing to note first, whether you're dealing with authenticating to infrastructure to service or software as a service or virtual machines or system to system connections, you always need to worry about authentication. It has never been a good idea to have weak or no authentication on services where you depend solely on the network to protect you. And in cloud environments, it is even worse, as I've already said, because a mistake or an oversight can allow untrusted internet connections. So even if you secure your network perimeter perfectly, you still have to allow users in. And a single mistake can allow a malicious user to take over something inside the perimeter and start attacking other things. So you do want to authenticate everywhere, both for humans and for system-to-system connections. The only thing you trust really is localhost, right? Don't trust the firewalls to keep you safe on it. Oddly enough, we call this zero trust, although that brings in a few other concepts, but it really should be called something like zero implicit trust or a little better. And it's also largely a marketing word that means almost anything you want it to. But the core of zero trust is don't trust something just because it's in a privileged spot, what you think is a privileged spot on the network. Go ahead and ask for credentials of some sort. So there's lots of good ways to authenticate both for humans and system to system. The first thing everybody thinks about is passwords. So despite the fact that everybody says passwords are dead, we're probably still going to have them for a little while longer, although they are, the demise is coming, I think. Passwords or memorized secrets that humans have to remember. Generally, my advice is use a long passphrase, right? So there's a famous cartoon, XKCD, correct horse battery staple. But you usually just want to have diceware is what I use for mine in most cases. 5 or 6 randomly generated words. It's a little much to type, but they're extremely secure and easy to remember. So if you want great details, by the way, on different attacks against passwords, there's a guy at Microsoft who wrote a terrific article called "Your Password Doesn't Matter." If you want to hear about like different types of passwords, that's a good read. I do disagree with the title. I think passwords, the password you pick does matter somewhat, but it's still a good read. There are debates as to whether or not passwords should be rotated regularly. So like some of the later NIST guidelines said, you don't need to rotate them regularly. Proponents say it helps mitigate the risk of password leaks you didn't know about. Opponents say it causes people to pick worse passwords. There's merits to both arguments. But I think everybody can agree that passwords should be rotated whenever you suspect that maybe they've leaked. And you shouldn't reuse passwords across different services, of course. It's just like general public service announcement. Practically speaking, the biggest problem with passwords is that they just are terrible because lost and stolen credentials are attackers' most used tools for many years running. So generally speaking, you want another factor, either something you have, a physical object you have. This is the standard 2FA stuff, right? Something you have or something you are, like your fingerprint. So
Chris, sorry,
yeah.
There's a question here.
Yeah.
In terms of data interoperability, wouldn't it make more sense to have like one authenticating system, like one system that you can kind of travel around the internet in and use? Or does that put you at risk of security vulnerabilities?
No, that's a good question. And you can, in fact, use the same type of thing in a lot of cases. Generally speaking, that's something like hardware security key or a FIDO2 authenticator. So like we have these, right? And you've probably seen these, this particular one's a YubiKey. And so you can register that same key with a lot of different sites, and you have to physically have the key, and you have to, physically push the button on it. So somebody can't just like take control of your computer. And then you can register that with a lot of different sites, and you can have a couple of them as backups, or you can use, a password plus a one-time password as backup. And that's where passwordless is really starting to make inroads, is with those types of FIDO2. Is that what you mean? Like using the something you have around? I think by the way, it'll grow to your cell phone as being your primary authenticator for most things, because people keep them around and they know about them. Is that what you're talking about? Or are you talking about?
Yeah, no, exactly. Because I mean, doesn't that solve or help solve the problem of interoperability, where like now consumers can be empowered to actually control their own data across all these different sites?
Yeah, well, there's a couple.
Their PII in one secure vault.
Yeah, so that's a slightly different. You're talking about something like distributed credentials, and that is sort of up and coming. I know that IBM has a solution, and several other companies have different solutions for that, where it's privacy protecting. So you have your own like wallet, and you can use it to authenticate yourself, but not give a whole lot of PI info out. So there's a privacy component to that with those distributed identities, and then there's also the authentication piece to it.
Does that increase security?
Yes, yeah. I mean, almost anything is better than a password, to be perfectly blunt, right? So those types of things are usually cryptographic based, where you generate a cert and you use the certificate, and so only you use the private key that you have, and only you have to do it. But like for these keys, they can even have what's called discoverable credentials on them. So they're privacy enhancing in that you don't have to necessarily give a bunch of information to it. You just say, I've got an account here, and then it can tell from just the credential that you have that account and authenticate you without giving a bunch of other information. So theoretically, you can do that without even giving like your email address or, just a generated username. So yeah, good question. There's a lot of intersection between authentication and privacy concerns, and they're a little bit at odds because authentication is wanting to know who you are, and the privacy concerns are often around not giving away too much personal information like that. But there are some up and coming ways to handle those types of things where you can authenticate without giving a lot of info. Did that answer your question?
Yeah, he's fine.
Great. And thank you. Like I've been talking for an hour now, and finally somebody gave me a break by asking a question. If you have any others, please chime in. So I'll continue here. Well, we talked quite a bit about second factor, and I think most people know something about the second factors. The only thing I'll point out is that if it's something people are using fairly regularly, it is kind of important to have it as a low friction thing where it's not taking a whole bunch of time and effort to do it each time. And the password list really does have the ability, I think, to do that. So I'm actually a pretty big fan of the 502 standard. So with 502, you can have a roaming authenticator like that YubiKey that you use, and you can plug in anywhere and use it. You can also register like your individual phone or your individual computer or whatever. And then several companies, Apple included, are doing things where you can register once, and then that registered credential can be synced to all of your devices, so that from any of those devices, once you've registered, you do it. You're at that point tying yourself to the security of that enterprise, but they have an awful lot to lose. And so for general consumer type stuff, it's probably a pretty good bet. So I guess I would sum this up as for humans, I think password lists will in fact start making bigger strides soon, because it's getting to a critical mass of being authenticated everywhere. And again, I think eventually, your cell phone will be what you use to authenticate yourself most of the time, unless we get to the point of like embedding chips in your hand or something. So you also do have to deal with system to system though, authentication. And so passwords and API keys can be used there. You do have to be careful for system to system, because you end up with a problem called secrets management, where if you leave that password lying around like just in a data file or something, anybody who gets into that system can get that API key, for example, and then use it. And a lot of breaches happen from that type of thing. In fact, there's a whole industry of people who watch GitHub for people to accidentally check in their API keys to GitHub. The API keys are usually called GitHub dorks, and I've seen like within about 5 minutes, somebody takes that and starts using it for whatever gain they can. So you do have to, you have to worry about where the passwords are being held for system to system authentication. One minor note, by the way, I mentioned API keys, which are basically equivalent to a password, but essentially unguessable because they're randomly generated. Tokens are similar, and they're often used as part of authentication systems, particularly federated ones. They usually have the benefit, they're kind of like an API key, but they have the benefit of expiring after a short amount of time. So they're a little safer to pass around, because if somebody gets one of them, it's only useful for a certain amount of time. So there's a digital signature on it. You get the token, and there's a digital signature on it that theoretically can't be forged unless you have the signing keys, and it'll say not valid after such and such time. So that reduces the risk of tokens. And tokens are often, even in cases where API keys are used, generally speaking, you have to take the API key to a token service, you get the token, and then all the other services accept the token and not just directly the API key. And that reduces the risk. If any one of those services gets compromised, the person compromising that service can use those tokens for a short amount of time, and then they all disappear. They don't actually have the API keys. One new thing on this list, by the way, that you may not be familiar with is identity documents. So a lot of cloud providers will actually have a service that the virtual machine can call, and then the provider will give that virtual machine a digitally signed credential. This is actually reaching out into other areas besides just virtual machines. There's a interoperability protocol called SPIFFE. And so like you can have your container orchestration environment like Kubernetes, and Istio as a service mesh can issue certificates to its stuff. Virtual machines can be issued certificates from their cloud providers. You can put them all together and allow like this virtual machine to authenticate this container and this database, for example, all using the same type of SPIFFE certificate. So it's not in heavy use yet, but I think it'll become a lot more important. So rather than passing around API keys and worrying about the secrets management problems of keeping those, you'll be able to say, well, I have to trust my cloud provider because if they're compromised, I'm already in trouble. And I have to so I trust this cloud provider and this cloud provider and this cloud provider or cloud orchestration or whatever to generate these certificates. And then I can get away for those to be cross-trusted so that a container can call a VM or a VM can call a database or so on without having to actually give them passwords. You can just say, I'm going to authorize this machine to talk to this database, and they take care of the authentication themselves. So sounds like magic, but there's some decent science behind it. Note, by the way, that automation can't use multi-factor, so it can't generally hold a device or have a fingerprint. There's some minor exceptions in that you can, like for synthetic monitoring, you can give it a TOTP, a one-time password in some cases. But generally speaking, automation can't. And so a good way to guard against leakage of credentials for automation is to say, not only do you have to have it, but in addition, you have to be coming from this particular IP address. So you wouldn't want to trust something just because it's coming from that IP address, but it's not a violation of zero trust or of good principles to use that as an additional factor in addition to the other authentication you do. Authentication can be centralized where all the systems or components relay requests to a central authentication store. They can also be decentralized. So it's where it's got its own list of password hashes. I did mention secrets management. I think I'm running a little, how am I doing on time here? I'm getting,
Yeah, I think
getting late, right?
yeah.
So yeah, I did mention a few of those things. I do want to spend just a minute on vulnerability management because it's very important. And let me go find my notes here. People get caught by vulnerabilities all the time, right? And so some of them are kind of unavoidable, like a zero-day critical unknown exploit and something that you're using externally. That happens occasionally, but most people have big problems just because they either didn't know about the vulnerabilities or didn't prioritize them. So if you look at the shared responsibility model, one of the most important things to know is which areas you're going to have to do vulnerability management on. So for application security, you got to make sure your code isn't vulnerable that you're writing. For middleware and databases and stuff, if you're installing them yourself, you have to keep them patched. If you're not, you still have to configure them properly. For operating systems and virtual machines, obviously you've got to install patches there. So just look down through the list of the stack that you're using and make sure you understand from a vulnerability management standpoint what you are responsible for. That's not a great treatment of vulnerability management, but it'll have to do for now. And the only other thing I'll add is network security. We already talked about VPCs and so on, allow lists, deny lists, those types of things. You don't necessarily have to run your own firewall anymore in the cloud. You can often just put a bunch of IP rules and things like that in network ACLs or in security groups. So network ACL guards the subnet that you're in. A security group guards the particular virtual machine, and you can use either or both together. And there's good reasons to use both of those. So, for example, if you have a class of machines that only needs to allow port 22 in, then you'll set up a security group, and that entire class of machines only allows port 22 in. You might also then have a wall around the subnet, only allowing stuff from a different subnet in. So it gives you a lot of flexibility in cloud. Most cloud providers have those same concepts. I think Azure calls them, like the naming in Azure is a little different, but generally speaking, that's available in almost any cloud.